Let's do a quick recap about classical mechanics. Actually, we are going to recap the one-dimensional motion of systems in classical mechanics. Suppose this horse is here and now this horse is going to move along this straight line. So if it moves along this straight line, its position is changing with respect to time. So its position is a dynamical variable. Its velocity is also changing because suppose when it moves, it is having a certain velocity, but when it stops, its velocity reduces, and when it stops eventually its velocity becomes zero, so its momentum is zero. So its momentum of this horse is also a dynamical variable quantity. If we think about the force acting on this horse, then the forces are, when it is standing, then gravity is there, friction with this floor is there. But when I am pushing it, gravity is there, this external force is there because I am pushing the horse to move, and the friction is also there. So force is also a dynamical variable. Its quantity, its amount changes with respect to time. This friction also changes because when it is moving on dry surface, the friction is more. But if I put some water on the floor, it will slip because then the friction reduces. So these are the dynamical quantities, and as the horse is moving in linear direction, so it is its translational motion. Any motion which is along a straight line is called a translational motion. So in 1D, state of any system, that is state of this horse, is specified by dynamical variables, position and momentum. Why they are variables? Because as I have just mentioned, their values are changing with respect to time. But some other dynamical variables are namely energy, angular momentum, etc. Because if force changes, then angular momentum is R cross P. If force changes, the momentum changes. If velocity changes, its momentum changes, its angular momentum is also changing. Let's have a look at this dynamical variable d, which is a function of position, momentum and time. For example, if I can write the energy of an harmonic oscillator, suppose I have a spring, and with that spring I have a mass, that is the harmonic oscillator, classical harmonic oscillator, and its energy is depending on momentum and position. This is potential energy term, because here force F equal to kx, k is the force constant of the spring. Then here energy is dependent on two dynamical variables, position and momentum. If we need to find out the value of this dynamical variable V, or for example in this case, if we want to find out what energy is, then we need to first specify the value of momentum and positions. Then we are only be able to tell the value of energy. But in quantum mechanics, the state is defined as, or is described by, the state vector. This is called wave function. This is a kth vector. I have written this as kth vector. This state vector contains all the information about the quantum mechanical system. For example, if we take an electron as quantum mechanical system, then this psi will have all the information about that particular electron. Suppose what is the amount of energy it has if it's residing on this state psi. So this is something which is very, very important. And this is a vector in a vector space. So let me compare the variables in classical and quantum mechanics. In quantum mechanics, a dynamical variable is represented by this d operator. We have just discussed the operators. Operators are denoted by this hat sign. And in quantum mechanics, what happens is this d operator will act on this state vector and will give me that particular value of this variable. So in classical mechanics we have position, in quantum mechanics we have position operator. Classical mechanics we have momentum, quantum mechanics we have momentum operator, or to be more precise it is px cap, py cap, pz cap, that is the components of the momentum. And a dynamical variable in classical mechanics is described by d, which is a function of x, p, t. These are dynamical, x and p are dynamical. And for quantum mechanics, this variable is described by the operator itself, and this operator is a function of x cap, p cap and t. X cap is another operator, position operator, p cap is momentum operator. And this is how energy differs in two mechanical system, in two mechanics. In classical mechanics it is just a scalar quantity, it is, in quantum mechanics it is also a scalar quantity. But what I am trying to say is, in classical mechanics this is only p square by twice m, but in quantum mechanics we need to write this as p operator square. So if I need to find out the energy value E, first I need to operate this p square operator on the energy state, then I will find out the P, and then I need to operate this this operator on the specific state psi. Then if I know this, then only I will be able to find out the energy value. But uncertainty is there, I am going to discuss it later.